Welcome to EE252 Electronic Devices and Circuits. Today we are going to talk about BJT small signal model and AC analysis. Specifically, in the previous lecture we said that uh, if you have an active linear two-port device, then you can use certain model to represent that uh, device. Instead of the whole thing, we can represent it by just 4 constant parameters. But the question is whether we can use the BJT as a linear active two-port device. We know that it's an active device. Also, we know that in most of the cases, it is a two-port device because you have, with respect to the common terminal, the other two are the input and output. So two-port is also fine. But the question is whether it is linear. So now today what we are trying to do is find out whether a BJT can be used as a linear device. If not, can we use the BJT as a linear device under certain conditions? So this is what we are going to do. As you already know, BJT, the transistor, is inherently a non-linear device. So how can you convert that into a linear device? Okay, so this is what we are going to look at today. Okay, so in order to do this, let's take a example. Let's take a small circuit like this. Okay, so we have a circuit, common emitter circuit. Okay, very simple one. Let me choose a signal source connected to this through a resistor, or this is plus VCC, RC, and let me call this RB. And this one, now let's include both the DC and AC components here. So let me call this VI, which includes both the biasing voltage as well as the AC signal. So this is basically, you can look at it as the Thevenin's equivalent circuit of the biasing circuit plus the signal source. Okay, so this is basically what it is. So you have voltages and currents. If you look at this voltage, this is the input to the circuit, which is simple V capital BE, which means both DC and AC. And you have current, simple I capital B, again it contains both the AC and DC components. This is IC, capital C, includes both AC and DC components. The output is V, simple V, capital C. Both, it includes both both AC and DC signals. So let me make that a point. So we have the VI, which is actually the DC component VBB plus a pure sinusoid Vs. So IB is basically capital IB, which is the bias current, plus the signal current IB. And IC, which is the bias collector current, plus the AC signal current. Okay, so let's initially do a DC analysis. Okay, let's first do a DC analysis here. We have, you can find the base current IB, which is equal to, you know, the DC component of VI is VBB, so we are only looking at the DC components of it. AC part we assume 0. So if I apply the Kirchhoff's voltage law to the input loop, That's this loop. Okay, so if this is the loop that we are considering, all the voltages that we have are this voltage, and this voltage. So since we are looking at only the DC components, this will be capital V B E capital. This will be IB RB, and this will be VBB. Okay, so IB, therefore I can write the expression and obtain IB to be V capital BB minus VBE capital divided by RB by just writing the Kirchhoff's voltage law above. So IC therefore is beta times IB, because I have ensured that this is in proper biased condition. Okay, now if I want to find the VCE, then I have to apply Kirchhoff's voltage law to the collector emitter loop. That's this loop, right? So what are the voltages that we have here? I have VCE and ICRC, which is equal to VCC. Okay, so that is simple. All right, so let me write that. VCC is equal to VCE plus ICRC. Therefore, VCE is equal to VCC minus ICRC. Right. So this is my bias point. So bias point or the Q point is IC and VCE. Okay, so both we have expressions for. Now what happens when we apply a small signal AC signal, a small AC signal also? In other words, when a small AC signal is superimposed, then all my quantities are going to be AC plus DC, whereas my VI now becomes VBB plus VS. So my how to find what is my simple I capital simple I simple B, that is AC quantity only. So how do I find that? Now we know the total current should be equal to, let's call this IS over beta times, this is using the Weber-Small equation but neglecting the leakage part. Okay, so this is e to the VBE over VT, capital VT, because it's a constant. All right, so this is my equation. This is roughly, and obviously you can have the minus IS over beta plus part also. Now what is this IS over beta? What we had earlier was just simple reverse leakage current, right? So IS. Now what's, you have to remember that in this is IB, so you could have used the reverse IB, but the problem there is that the transistor can be either in cutoff, active linear region, or saturation. When in saturation, IB can be arbitrarily large, and the IC does not grow beyond a certain value because it is saturated. Now this equation is valid only for the in this case we are going to look at it for the active linear region. So therefore the maximum base current that we need to limit is the maximum IC divided by beta, right? Because that is the beyond that IB can actually grow but IC will not. So therefore this IS is the maximum IC. In other words, this is the saturation current of the IC, and when you divide it by beta that is the current in the base at saturation, at almost saturation. Beyond that, if it goes to saturation, this is in active linear region, if it goes to saturation, IB now will be greater than beta IS divided by beta. So this equation, now this is very small, so we can forget about this compared to the first term. Okay, so we neglect that. So this IB can be written as just this part. Okay, but this is a non-linear. This is a non-linear relationship. Okay, this is non-linear. So this is you know, this is VT. What VT is the thermal voltage it's like 26 millivolts at room temperature. Okay, so now what this tells me is something like this relationship between VBE and IB. This looks like something like that. Something like this. It's an exponential curve. Now at a particular value of operating point where this is VBEQ and this is my IBQ, this is my quiescent point, that's this. So this is VCEQ, this is IBQ, this is ICQ. Okay, so this is equal to ICQ VCEQ. These are the quiescent conditions. Under such conditions, so these are my values. Now obviously this is not linear. Okay, this is non-linear. So but what I would like to have is a linear relationship. So how can you obtain a linear relationship from this? In other words, under what conditions this thing behaves like a linear relationship? Okay, because we need a linear analytical equation. We would like to have a linear analytical model for the transistor. Okay, so how can we convert this into a linear analytical model? Now we can use, so we can write IB as, because we know, we'll see whether we can do it. We know this component here is equal to VBE plus VBE. Okay, so let me use VBEQ plus AC and DC components. So let me use that here. So IB is equal to IS over beta, which is a constant, times e to the power VBE plus VBE divided by VT. Now here I am also assuming, if you remember, you had an n in this expression here. We had an n here. I'm assuming it's ideal and n is equal to 1. Okay, even if you have another equation, it doesn't really make much of a difference. It's just another constant, right? So what we have is something like this, expression like this. So I can write this as ISO beta e to the power VBE over VT times e to the simple VBE over VT. Okay, so I separate the AC and DC components. What is this? This component here is this is at the, let me put this as Q. Okay, this is at the quiescent point. This is at the quiescent point. So therefore what you have there is my base current at that point. So this is nothing but IBQ times E to the VBE over VT. Okay, this is what you have, right? Now this is still not a linear relationship. So what I'm going to do is I'm going to use Taylor series expansion to expand this. Use Taylor series expansion to write IB as IBQ times, and I'm going to expand this exponential term using Taylor series expansion, 1 plus VBE over, simple VBE over VT plus factorial 2, 1 over factorial 2 VBE squared over VT squared plus many higher order terms. Okay, so this is my expression. Now this is only, this only works, this will converge to exponential function only when this term is less than 1. If VBE over VT is less than 1, or when it is small. If it is not small, so this will not, if it is greater than or equal to 1, then this will not converge to the exponential function we had here. Okay, so therefore we know that VBE should be less than VT. What is VT? 26 millivolts at room temperature. But if it is closer to 1, then what happens is this term here will not be small. It will, you need to consider that also, in which case this will not become a linear equation. So in order for you to make this a linear relationship, okay, what should you do? If it is linear, all these parts from here up to this has to be 0, right? So you will end up with just these two components, which is linear relationship. It's a linear part. So under what conditions will this be linear? Okay, to make the relationship linear between VBE and IB, okay, in order to make this linear, VBE should be much smaller than VT. Okay, now the previous one, this is for VBE over VT less than 1, but it's not enough that VBE is less than VT. In order to get rid of these higher order terms, we need to make sure that VBE is much smaller than VT. Okay, so this is equal to 26 millivolts. So as a rule of thumb, we typically say if VBE this is a rule of thumb, when VBE is less than 10 millivolts, it's about 2.6 times smaller than this, which is not really negligible, but we are happy with that. Okay, at least it's better if it is even smaller, maybe less than 2.6 millivolts would be the best, but to be practical, we normally select this VBE to be less than 10 millivolts. Then what we can write is IB is equal to IBQ times 1 plus VBE over VT. Now it's a linear relationship, ignoring higher order terms. Okay, so now this is equal to IBQ plus IBQ times VBE over VT. IBQ, so you know this IB is equal to IBQ plus simple IB. So therefore this term has to be my simple IB. Okay, so therefore IB is equal to IBQ over VT, which is a constant, times VBE. That's my expression. Now this is clearly a linear relation. Okay, now when can we use this? When do you have this linear relationship? When the signal is small. Okay, VBE should be small, very small. Okay, so therefore we call this a small signal model. Okay, with this small signal model, we have IB, which is AC plus DC, is equal to IBQ plus simple IB. Therefore, and also we have VBE is equal to VBE Q DC part plus simple VBE and AC part. Similarly, if you multiply IB by beta, I will have IC, which obviously now will have ICQ beta times IBQ plus beta times simple IB, which is equal to simple IC. And similarly VCEQ, simple, so this is total VCE is equal to VCEQ plus VCE. Now you see all these quantities can be separated into AC part and DC part. So this is my DC part and this is my AC part. This is my DC part, AC part. Okay, so all these can be separated into AC and DC. Also, all my relationships will be linear. What? Under this small signal model. That is when VBE is less than 10 millivolts or more. It should be much less than 10 millivolts. Okay, so under such conditions, this actually, the BJT actually behaves linearly. The BJT behaves linearly, so we can use it as a linear active two-port device. So let's try to analyze this circuit now. The previous circuits, with this knowledge, under these conditions where you have small signal, first we need to do the DC analysis. In other words, to find the Q point, which we already actually did. So to do that, apply Kirchhoff's voltage law to the base emitter loop. We have VBB minus IBQ RB minus VBEQ equals to 0. So let me mark this as 1 and apply Kirchhoff's voltage law to collector emitter loop. Have VCC minus ICQ RC minus VCEQ equals to 0. So let me mark it as number 2, equation number 2. So these are the DC conditions, and this actually defines the DC load line, okay, because this is a relationship between ICQ and VCE, IC and VCE. Okay, so this basically defines the DC load line. So DC load line would look something like VCE is equal to minus IC. The proper form, IC will be equal to minus VCE over Q, VCE over RC plus VCC over RC. So that will be your load DC load line. Rho AC capital, this is AC and DC. So this looks like something like this, where this is my VCC, this is VCC divided by RC. The slope was minus 1 over RC. Okay, that is your DC load line, and my Q point is somewhere here. Okay, this will be my VCEQ and ICQ, and this is my Q point, right? We know all that. Now the next thing is we need to do the AC analysis. So for the AC conditions, again we apply the Kirchhoff's voltage law to the base emitter circuit. So that this is when both AC and DC signals are there. So in which case we will have, this is when both DC plus AC available. You have the same equation, but VBB plus Vs is equal to, plus, actually rather minus, simple IB, which is IBQ plus simple IB times RB minus VBEQ plus VBE, whole thing is equal to 0. So this is basically applying the Kirchhoff's voltage law to the base emitter loop when you have AC plus DC signals. Okay, this is the whole signal. So this gives me, let's separate the AC and DC components. VBB minus IBQ RB minus VBEQ, that's the DC part, plus Vs minus IBRB minus VBE equals to 0. But you see, this component here from this equation 1 is the same as that, so that is equal to 0. Okay, so equals to 0 from 1. Okay, so therefore I can easily write Vs from this equation, this part should be equal to IBRB plus VBE. Okay, that's my AC part alone. So now I can separate the AC and DC components like that in this case. Okay, similarly, if I write the KVL to collector emitter circuit, I can write VCC, which only has a DC component, minus IC, simple IC, capital C, IC RC minus simple V, capital C E, equals to 0. Okay, this is equal to 0, but this is equal to VCC minus ICQ RC, because this is equal to ICQ plus IC, and this is equal to VCEQ plus VCE. Okay, so if I separate those out, ICQ plus minus VCEQ, so this is the DC part, minus IC, simple I, simple C, RC minus VCE is equal to 0. And again from equation number 2, we see this part is equal to 0 from 2. Therefore, I can write this part has to be 0 also, because that is this. Okay, so VCE now is equal to minus IC RC. Now you see, this is the load line for the AC component. This is the AC load line. This is the AC load line. This defines the AC load line. Right. Now, what can you say about this? Now, AC load line cannot exist on its own. Unless it is properly biased, there will be no AC load line. So, therefore, AC load line has to pass through the DC load line, the quiescent point. AC load line should pass through Q point also. So this is basically, this is the superimposition of AC plus DC components in the circuit. Okay, so the load circuit has two components, AC part and DC part. So this is AC load line represents both. Now what do we have? Now we obtained a linear circuit or linear model for the BJT under certain conditions. We said small signals when VBE is less than 10 millivolts. So under such conditions, so with this we have a linear active two-port device. So this BJT acts as a linear active two-port device. So active because it is powered by an external battery VCC. Two-port, there are only two ports, input port and output port. Input port is between the emitter and the base. Output port is between the emitter and the collector. Those are the only two ports that we have. Linear because under specific conditions, that is VBE, simple VBE is less than 10 millivolts, this behaves like a linear circuit. So what are some of the assumptions? So this tells me I can write this circuit, I can draw this circuit like this. Okay, this is my input port, this is my output port. Okay, so two-port device. This is my input current IB, this is my output current IC. Mind that I'm only using the simple terms, the AC conditions. Okay, so this voltage is VBE and this voltage is VCE. Okay, this is my linear active two-port device. So if you look at it like this, you have what you expected in a linear active two-port device. However, there are certain assumptions we need to note. Assumptions for this to actually work. One, BJT is in active linear region. Okay, so it is properly biased and properly biased. When the AC signal is applied, it doesn't go into saturation or cutoff, and the signal is small enough. Signal is small so that the parameters are constant and system behaves linearly. We'll get back to this. Number 3 is, though we do not go into too much details, the frequency of the signal is small. This is a low frequency signal. The reason for this is, if the frequency is high, there will be other, in addition to these parts, there will be parasitic capacitances between different terminals, and this would change the behavior of my circuit. Now let me come back to this statement, parameters are constant and system behaves linearly. So you looked at the behavior of VBE versus IB. So it was something like this. It was an exponential curve, and we said this is its Q point, IBQ, VBEQ. And we said my signal only changed. So this is my Q point, and my signal changed only. So if this is 0.7 volts, that is 700 millivolts, it has 700 millivolts. My variation was small, so within 10 millivolts, so something like this. Okay, so only very small variation. This was the VBE. Okay, this is less than 10 millivolts. So you can see in this region, you can see that if you take the slope of this, okay, the slope of this curve at this particular point, whether it is at this point or this point or this point, it remains roughly the same, though in general if it changes with the point, at this particular point around the Q point, if you choose the variation to be very small, then the slope is constant around Q point for small VBE changes. Okay, so this is what we call parameters are constant. So the parameter here is the slope of this. Okay, so it doesn't change too much. And your DC load line and the AC load line, if I draw again, this is VCE IC, this was your DC load line, this was your Q point. For this particular case, you will see that your AC load line passes through this, and what was the slope? Slope was also, so this is IC equals to minus 1 over RC VCE. Okay, so therefore the slope again is the same in this particular example. It could be different in general, but in this particular example is the same as that. This is my AC load line. Okay, so what you had earlier, this was the DC load line, so they are the same in this example. Okay, so this basically tells me what are the conditions that I need to satisfy if I were to use the two-port network theory for my BJT. If I want to consider my BJT as a two-port active linear circuit, I need to ensure that my frequency of the signal is small so that the parasitic capacitance effects do not interfere with my model. Number two, the signal is small so that VBE is less than 10 millivolts, if preferably much smaller, so that the parameters that is H11, H12, H13, H21 and H22, those parameters do not change much. In the next lecture, we will see how you find those H11 and H12, those kind of things using transistors characteristics, input and output characteristics. But so these are the parameters, these are the H parameters that we are talking about. They are constant for the operational range when the signal changes, though in general they can change for larger signals. And the other condition is that the BJT has to be properly biased, and it should not go into saturation or cutoff regions during my operation. Okay, this is all for this lecture. Thank you.